All right, thank you very much. This talk is going to be a little bit different. It's not an applications talk. This is a system software related talk. Bill is the PI. I'm the local PI from Argonne. Rajiv Thakur is also involved in this work. The proposal is talking about system software for scalable systems, but really this part of the work is building a stronger, faster MPI for the Blue Waters system. I presume everyone over here knows MPI, so I don't have to give that background. This will be going to be a little bit detail of MPI, so if you have any questions, feel free to stop me at any point. Okay, all right, so I'm not going to give much of a background, but most of this work is related to using the cores of the Blue Waters system, or actually any multi-core, many-core type of system more efficiently. So the Cray, for example, has 16 cores. Other machines, BG has 16 cores, 64 hardware threads. That number is going on increasing, at least to a certain extent. And there are two ways applications are trying to utilize these models. There are many ways, actually, but two ways that I'm going to concentrate on. The first method is to have not just one process, one MPI process for every core in the system, but to have one MPI process for the node and have a bunch of threads doing most of the computation. Okay, that's one model. There are many reasons for this. For example, the resources associated with on the node, they're not scaling as fast as the number of cores. Memory is one example of that. The other examples too. So you want to have a sharing of these resources, and threads are a good model to do that. That's one reason why people are using them. Many other reasons. The other model that I want to point out is what are being accepted on some machines called as a system cores. These are not cores that are exposed to the application. These are cores that are handled by the system software for doing extra things. Okay. On the BlueJean, for example, there is a core, 17th core, extra core that's kept aside, in hardware that you can put system software on. On Cray, there is no such extra core kept aside, but you can envision keeping one of these 16 cores aside. It's not you lose the perfect square number by making 15 cores, but you get the idea. You can have, out of 16 cores, if you keep one core aside for system software tasks, it's not that big a deal. So I'll be talking about these two models. One is the threading model and how we have tried to improve that. The second is how to utilize one of the cores on this Cray machine to behave as a system core, something to do extra processing that application is not aware of. So first, let me talk about the threading model, MPI plus threads. MPI itself, just a little bit of background on MPI. MPI provides three ways really, to interact with threads. The second, third, and fourth in this list. The first is called as a funneled mode. There are a bunch of threads. There's a process, bunch of threads. All threads do the computation, and one thread does MPI calls. Okay, very simple model. A lot of people use it. Not a great model, because when one thread is making MPI calls, all other threads are idle. Not a great model. Second is serialized. Any thread can make MPI calls, but one at a time. Again, not that great a model, but it's very widely used because it performs very well. The fourth model is what I'm really going to talk about, thread multiple model. This is the most generic model for MPI and threads interoperability. Okay, so you have a bunch of threads. Any thread can make MPI calls at any time. One thread is doing a send, another thread is doing a receive. All that works great. Okay. However, there is a cost associated with it. MPI internally has to do a lot of bookkeeping. It has to do logs. It has to do atomic operations and so on. To keep the stack consistent, there's a lot of work associated, which costs some performance that we have to deal with. So there are many reasons, even though there's a performance loss associated with it, people are still moving to this thread multiple mode. There are many reasons for this. One reason is, actually the biggest reason why people are using is to make their code uniform. Okay, they don't want to have a special thread saying only this thread can make MPI calls. It's a big nuisance for them. They want to have a bunch of threads. They're doing all the work. They're doing MPI communication any point of time. Everything works great. That's the vision, at least, right? That's what they want to do. So that's one of the reasons they are using. Another big reason is, at least on InfiniBand and BlueJean type of systems, the network communication performance depends a lot on how many cores are driving the network. Okay, this can be done with threads or processes, but it's a little simpler with threads because they can coordinate with each other a little better. So when you have all of them driving the network performance goes up by almost 4 or 5 times improvement in performance, especially for middle-sized messages. Okay, so we have a bunch of applications that are moving to this model. So we wanted to study and see how does the Blue Waters system do for these kind of applications. Is the system ready to be able to handle such applications? Okay, so we started with Graph 500 as a case study to understand how this works, and it's primarily because of 2 reasons. One, it's irregular, which is good for threading models because if they share all the data, which means irregular computations can work a little better. There's better load balancing of things going on. Second, it's communication intensive, which stresses the MPI layer a little bit, so that helps us to understand what bottlenecks we have in the MPI stack. All right, so for people who don't know how the Graph 500 benchmark works, it's a breadth-first search algorithm. So very simple, you start with a root vertex and you try to see at each level what vertices can I reach with 1 hop, what vertices can I reach at 2 hops, 3 hops, and so on, till I reach all the vertices, okay? So I start with 0, let's say, and then I say, okay, what are these? 1 and 2 I can reach with 1 hop, then I go and say 6, 5, 3, 1, 4, these I can reach with 2 hops, and finally, last vertex I can reach with 3 hops. Okay, that's basically what all it's trying to find. Okay, it's a graph problem. It's very widely used in social networks, for example, to tell who your friends are, right? Recommendations of friends. This is exactly the algorithm that's used. Okay, it's very widely used, and it's a very irregular and communication intensive algorithm. So we took this, we ported it to MPI plus threads, and tried to see what happens. We took the exact same algorithm, no changes to the algorithm. We took processes and just mapped them to threads. So each thread has its own communication buffers. Everything is exactly like processes, but now they can share all of the data. So all of the data on the node is shared by all the threads, so there is no communication inside the node, or no explicit MPI communication within the node. So you can see over here, by changing this algorithm, everything just gets better. Amount of data reduces a little bit. Number of messages exchanged drop significantly. So the model is better in general, but the question is, in theory, it should perform well. How does it do in practice? So we tried that out. I was wondering if someone will throw something at me for doing a Blue Waters versus BlueJean comparison over here. So it's not meant to be a comparison. That's why I put different scales so that you can't directly compare those two. But the idea is, it's the reversal of trend that I want to showcase over here. On BlueJean, things are as expected, right? It's execution time, so lower is better. We have processes. They're sending more messages, more data. Threads sending lesser messages, lesser data. Great, performance is better. Okay, that's great. If you look on the Cray Blue Waters machine, I have processes are sending more messages, but the performance is better, right? Execution time, lower is better. For threads, it's higher, it's worse. Okay, so something is going wrong. Something is nasty is going on over here. So we went and tried to understand what's going on the Blue Waters machine. What's changing? What is this reversal of trend? That's totally unexpected. Right? This is what we expect, right? So we went and looked, and we did some analysis. I should have put these pictures at the start. We have 4 cores, 4 processes talking to each other versus 4 threads on a node on 4 cores talking to each other. We did this experiment, compared this performance, and we have this huge gap in bandwidth between threads doing communication versus processes doing communication, okay? Big difference in performance. So we went and digged a little bit more to find out what's happened, and turns out the problem is not the Cray MPI stack itself, but the fact that it uses a Linux kernel. Okay, and it's a problem with the Linux scheduling algorithm. I'll talk about that in a minute. So just so you understand how the MPI stack works, this is what happens. Okay, I said in thread multiple mode, it's easiest for your application perspective. Any thread can do its computation and do MPI calls at any time. Okay, there's no coordination required. That's great from the application perspective, but MPI internally has to do work to keep the stack consistent. So the way it does it is, you do a MPI call internally in the MPI stack. You go and do critical sections, locks, or some other form of critical section to make sure that the stack is not overwritten by 2 different threads. Okay, that's extra work that MPI does. That, of course, can cause contention. It can cause extra memory barriers. Can cause a lot of other overheads. Okay, so that was what we looked at. That could be a possible contention, but in reality, that didn't really add too much overhead. What what added the overhead was the scheduling. Okay, the way the Linux kernel works is that your scheduling is kind of biased towards the thread that got a lock. So if I have two threads, let's say, and both of them are trying to grab a lock, what was happening is the first thread that grabs the lock, okay, checks, sees, do I have any work to do? Okay, I don't have any work to do, so it gives up the lock and tries to get the lock again. Okay, all threads are doing that. What's happening is the first thread that gets the lock keeps getting the lock again and again, even if it has no work to do. So what's happening is I'm a thread, I get a lock, I see, I have no work to do, release the lock, try again, I get the lock again. Again I look at it, there's no work to do, give up the lock. So this entire thing was causing starvation of all the other threads. So we did this analysis. We noticed there's a big starvation. In some cases, all 15 threads are starving for a long time. We have some more details on this if you like. So we looked at that and we wanted to minimize that. This is how the API stack works. I don't think I'll go into that details. We implemented a bunch of algorithms. Now we emulated this. This should have been inside the MPI stack, but Cray is very protective of their stack. They don't want to give out the source code. So we went and tweaked around with this. We emulated this. We used the original MPI stack to do this emulation. So it doesn't use the high-speed network in these experiments, but for the on-node experiments, I don't think it matters so much. It worked fine. We improved the performance quite a bit. How much is that? 2.5x, something like that. We did first a ticket lock, which is a fair lock. First of all, you don't have the starvation problem. Second is a prioritized lock, which prioritizes threads which have work to do, rather than arbitrarily letting the OS schedule whoever it wants to. Okay, those are the two things. These are not the ideal goal. The ideal goal is what is called as a message-based thread activation, which says when I get a message, I know this thread, this message belongs to this thread, so I'll wake up that. That's the ideal goal, but we haven't gotten to that yet. But this is where we are so far. We did some experiment, got some improvement. We are working with Cray to try to see if they can incorporate that into their stack. It's going to go out in the original MPI-CH stack this November at SC, which means sometime next year Cray is going to pick that up. So Blue Waters 2 is where you'll get those algorithms. Okay, the next that's one part, the threading part. The next part I'm going to talk about is how to use this extra helper core, extra system core that I can use to support some of my operations to do better on the system. Okay, so before I talk about that, let me give a little bit of background about the MPI one-sided communication. How many of you here have used one-sided communication? Show of hands. Like 5 people, 6 people. You don't count. 7 people. That's good. So actually, I was expecting like 2. So 7 is great. So one-sided communication it's been there since MPI 2, but it's significantly improved in MPI 3, and it's available on your Cray, the latest MPI stack on the Cray. You should try it out on the Blue Waters machine. So the way it works is that every process allocates a bunch of some amount of memory, which is when you allocate it's private. Okay, then you take that memory and in some sense declare it as publicly visible. Okay, so you do that. Some of that will be remotely accessible. Then that remotely accessible memory together forms a global address space in some sense. Okay, now this memory, every process can access its local memory, its local private memory, or any of the global remotely accessible memory. Okay, local memory, of course, it can do load store operations. Remote memory, it can access with a put, get, or update sort of operations. That's the basic idea of one-sided communication. I have some pretty animation which I drew like 6 years ago. I'm going to use that. In two-sided communication, the receiver posts receive or I receive or whatever, and sender sends a message. The MPI stack sends this message. There's a matching going on the receiver side, and you put the data into the memory buffers. That's how two-sided communication, send receive works. When you send a message, a receiver has to explicitly receive the message. One-sided communication is better. The sender side just tells both the origin address and the target address, and MPI stack takes the buffer from the origin side, takes the data and puts it on the target side. No interaction from the remote target. Okay? In theory, that's how one-sided communication is expected to behave. However, in practice, doesn't always behave that way. The main reason is here you're assuming that when I say I don't have any interaction from the target side, data is automatically put in the target buffer. It's not magic, right? Someone has to do the putting of the buffer. Usually, we expect the hardware to do most of this depositing of this buffer on the target side, okay? Hardware can only do so much. It can't do all operations. It depends on what you're doing. If you're doing a contiguous put or get operation, hardware can probably do it for you. If you're doing a three-dimensional subarray accumulate on the target side, hardware is probably not rich enough to do that just yet. Maybe the next generation will, but not just yet. So what happens in such cases is you use software to do these kind of operations, okay? And when you use software, what happens is the target side has to receive the message, some software on the target side has to actually do the accumulate of that operation. So that costs some interaction in the sense some CPU is used on the target side to do that. What this results in is a lack of progress that results in because of this. So if I have a origin P1 doing an accumulate operation on P0, if the P0 is stuck in some computation and I'm doing an operation that requires the target to do some work, like a 3D accumulate or something like that, this origin is delayed because it has to wait for that to finish. What I would ideally like to happen is I keep aside a system core, says I have 16 cores, I will keep aside one core to help me do these kind of operations, and I will just talk to that helper core which will do my operations for me. That's ideally what I would like to happen. Now, you can do this by putting a bunch of threads around, sitting around and doing this work, but that's very expensive. I just showed the threads graph where you lose a bunch of performance if you use threads. So we did a new design called as the ASP. I have no idea what ASP stands for. My student made up that acronym. But the idea is that we don't use threads for making progress. Oh, A might be asynchronous. I don't know what SP is. Sorry? Maybe, I don't know. That sounds good. Let's use that. So the idea is we don't use threads for making asynchronous progress. Instead, we use processes. Okay, it's a part of the MPI 3 standard. We designed what is called as shared memory between MPI processes. So MPI can expose shared memory to the user. So you still have processes, no threads, still have processes, but these processes can allocate a bunch of shared memory that all the processes can access. So it's a little bit different from threads in the sense that if you create threads, all data is public by default. You can move something to thread private storage to make it private. In shared memory model, all data is private by default. You move things into the public memory so others can use. So it's a little better model to use, plus it doesn't have any of the overheads of threading and so on. So the way this works, this is at the PMPI layer, so we didn't have to modify the Cray MPI stack. As soon as the user does MPI init, when you create COM world, we go and keep this helper process aside, where we create, these two are on the same node, P0, node 0, yeah. We create a shared memory region internally and map from every process memory to the shared memory region to the helper process. Okay, so every process allocates memory to be remotely accessible. I internally do some magic and map everything into this helper process address space. Okay, important thing to note, we are not moving memory, we are not moving data. The memory is exactly where it is. So if you have a NUMA node, it's exactly on the same NUMA domain that you allocated. It's just the address space is mapped to the helper process. Okay, it's a small distinction if you care about the mapping of the memory and so on. Doing that, we did performance comparison. This is with respect to the if the remote target process is blocked, idle for some time, what happens? How does the performance behave? This is the original Cray MPI stack. This is what we get with our MPI plus ASP model. Very good thing. You can do this with a thread-based progress as well. You can get the similar progress with thread-based progress too. But important thing to remember is the moment you have threads, you lose the performance. Okay, so this blue line would have been MPI ASP regular performance. This is the threads performance because of the locks that I talked about. But you have none of this threading overhead and you have all of the asynchronous progress. So best of both worlds. It's a little weird in the sense that the comparison is not perfectly fair because I took away one core, okay? But, well, you have 16 cores. Tomorrow you're going to have 100 cores. So it's okay to keep away X number of cores. It doesn't have to be 1. It can be more than 1. It can be like 4, okay? But hopefully that's going to be a small fraction of what you need. Another important point I kind of didn't mention over here is that whatever operations are done in hardware, okay, if you're doing a put-get operation that the hardware supports, there is no performance loss. The hardware will behave exactly the same way it was doing earlier. Everything that requires software interaction, that part is accelerated by this ASP process, okay, this helper process. Okay. There's a small distinction of that. All right, I'm done. So takeaway, multi-core, many-core are here. Cray Blue Waters is a smaller scale multi-core machine. Blue Waters 2 is going to be the real multi-core machine. So these kind of approaches are going to help with the, I guess, the next generation machine. Some of these are, the ASP is available. You can use it today on your Blue Waters machine. The threading model is not quite available. We hope to push it out in the original MPICH stack so that Cray can pick it up in the next version, actually 2 versions out. So hopefully you'll have all these to try out in your applications. Thank you very much, and I can take questions.